I'll begin with a word of prayer. Let's start here. Dearly Father, we thank you for today. I thank you for these students. And just pray you'd help us to use what limited time we have left. Amen. All right. So I will go and review what I have done so far. What I'm talking about is the matrix multiplication formula. How does it specialize in the case that either one of the dimensions is 1 or the middle dimension is 1? So in these special cases, the formula that I have up here that I gave as the general definition is a little bit specialized. First of all, if we have a row times a column, there is no index on AB. All right? Here the A is, in this, what I'm saying here is R is the A and V is the B. Okay? That's the case we're thinking about there. And so for a row times a column, we just have a dot product, which the summation notation formula for is right here. So that's the first case. That's kind of a outlier for the definition. The second case, which is kind of an outlier, is row times matrix. Right? Row times matrix works out to just have this general formula. As you can see, there's just one index. RA is a row vector, so we talk about it as jth component. And the definition of matrix multiplication in this case says that the jth component of R times A is just the sum k equals 1 to p of R sub k, A sub kj. We sum over the first index of the matrix being multiplied by the row vector. The next interesting case is matrix times column. So matrix times column, in this case, the output's a column vector. So again, we're only looking at one index for the answer, which I've used I for. And here's the formula for it. The ith component of matrix A times vector V is just the sum k equals 1 to p of A sub I k V sub k. And notice this time that we sum over the column index for matrix column multiplication. We sum over the row index for matrix row multiplication as it happens. Any questions so far? So these are just special cases, really, of, we already did. And then this one here would be something like what? This is a, what is this? This is what kind of multiplication we're looking at here. We're looking at a column times a row, right? Column times a row is actually a matrix. And so here's an example of that. Something like 1, 2, 0 times 7, 1, minus 2. All right? How does that work out? What it is, by definition, is that 7 times 1, 2, 0, concatenated with 1 times 1, 2, 0, concatenated with minus 2 times 1, 2, 0. I'm showing you a nice way to calculate it. Let me make the concatenation things dotted so that you can not kind of see the contrast of black on black there. So specifically, this matrix is 7, 14, 0, 1, 2, 0, minus 2, minus 4, 0. So yeah, you can take a column times a row and make a matrix like this. All right, so what's the general summation notation formula look like here? It's kind of funny. So we maybe would be taking a column V, right, times a row R in my current language. And I'm asking the question, what's the, we'd ask the question, what's the ijth element of that, right? And the funny thing is here, this is the P, right? P ranges from P equals 1 to P equals to 1. I mean, well, I should say K. K ranges from K equal to 1 to K equal to P equal to 1. That's probably better. I've been using K for the summation. The point is, K just sums over one value. So there is no sum in this case. To create this one, you literally just take the ith component of V and multiply it by the jth component of R, I think. Is that right? If we take 14, that should be what in my length. So this is my V, this is my R. I'm claiming that this VR what's this? This is the 2, 1 component. Allegedly, that's v sub 2 times r sub 1. Is that true? Yeah, it's 2 times 7, which is 14. Yeah. By the way, I'm not really deriving anything right now, to be totally honest with you. I'm just fully explaining the definition. This is what we mean by that notation. These are special cases of that notation. So I think it's healthy for us to talk about these special cases, since they might surprise you otherwise, right? Yeah. All right, any questions, I think? So was Convo very exciting today? No? No? You guys are... I'm not playing poker with you guys. That's mostly because I just don't know how, though. Let's see here. All right, there were things I was going to say here before I got distracted by this nonsense. If I could remember, that would be lovely. Tell you what, it seems like now as good a time as any. Pass that around. Thank you. Let's see here. So, we learned last time that we can build any vector from the standard basis, right? And we can build any any matrix from the EIJs, right? And if you watched the help session yesterday, you'll find out that there are many, many more relations between the big E's and the little e's. I'm going to collect together all of those for us right here. So this is theorem 2.3.27. Some of these we did last time. For example, V, you can write V as the sum I equals 1 to n of V sub, oh no, that is supposed to be sub I, E sub I. Well, there's a typo. Ah. All right, well, note to self, fix that. So here I'm assuming that A is in Rm by n, and V is in Rn, all right? And I'm sticking with what we introduced last time, that Eij, the kth component of it, was defined to be Kronecker delta Ik, Kronecker delta Jl, and of course the standard matrix E, E sub I, the jth component of that, also Kronecker delta Ij. Okay. So here's some things we can do. First of all, we can take any vector, we can write it as a sum of the standard basis. We can take any matrix, we can write it as a sum of the Eij's. What else can we do? We can take Ei transpose times A, and that's going to give me rho I of A. We can calculate A times EI, and that's going to give me column I, right? I can do that. I can do more. I can calculate the ijth component of A by Ei transpose A times Ej. All right. These are things we can do with the standard basis and the matrix units. Standard basis element. This guy is often called a matrix unit, or you might call it a, I don't know, that terminology is unfortunate because it's not a unit in the sense of abstract algebra. In fact, we'll learn that this matrix is very much not invertible. When we say matrix unit, we're meaning matrix unit because it's got a 1 just in one entry and all the other entries are 0. In that sense, it's a matrix unit. Unit's another word for 1, sometimes, in that case. Except when it's not. Sometimes unit's just used to say something has a multiplicative inverse, and those two usages are at odds here in this terminology. So, okay, anyway, and we also have this. If we take Eij and we multiply it by EKL, all right, that's equal to Kronecker delta JK EIL. This is also known. Furthermore, we can even build the matrix units. We can build Eij as EI times EJ transpose. You can construct the matrix unit from the standard basis in this way. And really, this is kind of the thing that weaves all these things together. I buried the lead. EI transpose EJ is actually equal to Kronecker delta IJ. So I can prove like one of these things, but I can't prove all of them, you know. I did a few of these yesterday in the help session. So let me just pick on one here. The one I think I stated AEI equals column I of A last time. Let's see here. So let's just discuss some of these. First of all, if I have, you know, E1 transpose times E2, suppose we're in R3. What's this? This is 1, 0, 0, right? Times 0, 1, 0. On the other hand, if you have E1 transpose times E1, you'd have 1, 0, 0 times 1, 0, 0, like that. Right? So you see that the top multiplication is what? What's the dot product of these two things actually? I mean, that's kind of the point, is that this is actually a dot product, you know. So this is an example of that last thing I wrote, which is that EI transpose EJ is in fact Kronecker delta IJ. What that means, of course, just to remind you, is 1 if I is equal to j, and 0 if I is not equal to j. But from another way of thinking, right, if you don't want to think about matrix multiplication, if you want to think about another way of thinking, you could say, well, really, it's just the dot product of the vector EI and EJ. That's what that is. So if you've had Calculus 3, what that says to us, at least if we're thinking about Rn, you know, if we take the case that R is equal to the real number system, then the standard basis is such that the dot product of any two of them is 0 if they're not the same, right? And it's 1 if they're the same, which is to say that they're mutually perpendicular and all have length 1. We'll get back to that later. Much later in the course, we talk about geometry and vector spaces. But it's worth saying that here. Okay, so let's try out. Let's calculate what is A times EI. All right. Well, I'm going to try to use some of those things together and just to show you how we can do these kinds of calculations. Now, I said that A is what? It's the sum. Oh, let me, instead of doing EI, pick any other letter other than I and J. What do you guys want? Anything but I and J. What's that? N? I try to save M and N for dimensions, so I try not to use those for indices. T? I'll take it. It's weird, but I'll take it. All right, T. ET. Let's see. Very good. Okay, so A times ET. So this is the sum over I and J of Aij, right? Eij times E sub t. Why? Because we proved last time that you can build any matrix from the matrix units, right? But what is this equal to? Well, Schneikes. I don't have that one. All right, I guess we'll have to get into the weeds. I'm actually going to have to think for a second. Don't worry, not that much. Aij. So we can build Eij from the little e's. How do we do it? What's Eij? Just so you guys are not lost, E12 is what? It is 1, 0, 0, 0 in the 2 by 2 case. Just 2 by 2 intermission. For my other example, just let's take a short intermission, make sure we all understand. This is what? This is actually, how do we get a matrix from a column and a row? Curses, I erased the one case I need to refer to. I have every case except for the one I care about. So the opposite, column times row, right? This is, in fact, column 1, 0 times row 0, 1. Wait a minute. I think I messed that up, didn't I? Oh, yeah, I see. This is fine. This, what is this equal to? 0, 0, 1, 0. Which is, by the way, what I should have written here. Right? The definition of E12 is it's got 0, 1, like that. Okay, so that's actually generally true, is the point. So this Eij, I can rewrite as, sorry, I buried the lead here. This is E1 times E2 transpose. In the same way, this Eij is EI times EJ transpose, ET. I'm assuming that we're working with a square matrix at the moment. If we were working with rectangular matrices, many of these things are still true, appropriately modified. But then I've got to use different bases for the different sides. I talked about that a little bit in the help session yesterday. It's really not. We'll cross that bridge again if it comes to us. This right here, though, what is this, guys? That's the row times the column, right? That's the dot product of Ej and Et. So that's exactly the Kronecker delta JT. So what does that do? That kills the sum over j. It just leaves us the sum over I of A, I, j, E, which remains, the I or the T? The j or the T? Which one am I keeping? So I already wrote. This is not right. I should say A, I, T, right? And E-T, I think. Right? So to be more detailed, this is the sum I equals 1 to, let's say, m. This is the sum j equals 1 to n. It's the summation over j which is getting killed by that Kronecker delta. This is sum I equals 1 to m. What is that, though? This right here, folks, is A1 T E T plus, let me just, I'm out of space, but that is exactly column, that's exactly column, column T of A. All right. So that's about all I have to say about it. I've assigned you some homework problems about these. I hope that they become yours after you work on them some. If you got questions about the EIJ or the lower E notation, come ask me. We have a help session next week again, and I have office hours, et cetera, et cetera. I'm going to go back to transposition again and look at some additional questions. One of the additional properties of transposition, so we saw the elementary properties before. We saw that the transpose of the sum is the sum of the transposes, and we saw that we can pull scalars out of the transpose. We did all of that before we had matrix multiplication, right? But the really neat thing is matrix multiplication and transposition, they behave strangely together. If I take two matrices which I can multiply A and B, all right, and I transpose them, it turns out that that's equal to B transpose A transpose. So this is often called the socks-shoes identity, because it's kind of like, you put on your shoes first and then your socks. Wait a minute, no. Most of us put our socks on first and then we put on our shoes. But when you undo it, it's the opposite way, right? So, actually, this is also true for matrix inverse, which we'll get to before too long. But now that's a homework problem to prove that. How should you prove that homework problem? You want to use index notation, all right? So this is a good test of whether or not you understand the index notation, if you can actually work your way through that. But that's your homework to prove that. Now, let's see what that says, though. See, once you know that, if you prove something like A times E, let's say, T is equal to, man, that's weird, column T of A, what would happen if you take the transpose of this equation? Take the transpose of that. What does it say? Oh, I can't, see, this is why I can't commit to the T any longer, because as this and this and no, I'm sorry, I'm gonna have to bail. I'm gonna go to I. So A times EI, and there are other books that use the lowercase t for transpose. So it's, yeah. What's the transpose of the ith column of A? If you look at the definition of transpose, it is the ith row of A. All right? Well, yeah, it is the ith row of A transpose, in fact. And what is this? Well, by socks-shoes, this is EI transpose, right? A transpose. So if you just say, okay, so let B equals to A transpose, then we find that E sub I transpose times B is the ith row of B. So if you can prove that the matrix times the ith standard basis is the ith column, then the socks-shoes principle, socks-shoes identity, gives you the corresponding row identity for left multiplication by a row. This is often the case. If you can prove some identity for column vectors, if you take the transpose of the identity, you'll obtain a corresponding identity for row vectors. Pretty neat. Oh, well, it's okay. Do you guys remember what a symmetric matrix was? A, Rn by n, symmetric, if and only if A transpose is equal to what? A, right. So what if you had a symmetric matrix? What if you look at the eighth, here's the question. Is A to the power k also symmetric? So So what about the kth power of that matrix? And by the way, what is the kth power of a matrix? I probably should define that. Definition: a to the 0 is equal to the identity matrix, right? Which I have not defined yet, annoyingly. And a to the power k plus 1 is just equal to a times a to the k for k greater than or equal to, well, for k in the natural numbers. This just means that a to the first power is a squared is a times a cubed is a times a times a. It's the usual definition. Now what's I? Sorry, I got the cart before the horse. So this is a matrix. This is the identity matrix. N by n, and where the ijth component of I is equal to the Kronecker delta ij. So it's a matrix which it's called a diagonal matrix because it only has non-zero entries on the diagonal of the matrix, on the 1, 1, 2, 2, 3, 3, so forth components. So I don't want to do it right now, but there's a theorem. You can prove that the identity matrix times any matrix is equal to the matrix again, and likewise, the matrix times the identity matrix is equal to the matrix again. That's why it's called the identity matrix. If you multiply it by any other matrix, it just gives you the matrix back again. Very boring. It's the analog of the number 1, except for matrices. But this notation is ambiguous, of course, because the identity matrix, it's not just one thing, it's a lot of different things, right? Like, you might use sub 2 to indicate it's this one, right? Or this one. 3 by 3 is like this. Right. Okay. That's the identity matrix. So let me get back to back to my question. Is a to the k symmetric? So how would we prove that a to the k is symmetric for any n in the natural numbers? I mean, for all k in the natural numbers. What proof technique would you use to show this? Induction. Very good. So let's do that. Here's the proof. K equals 1. A transpose equals to a to the 1 is equal to a, right? So, which is equal to a to the 1. I'm sorry, so what's the induction? Sorry, guys. So our induction claim, let me write it out, is that A transpose, A to the k transpose is equal to A to the k for all k in the natural numbers. Right. Let me call this claim star without the for all. Just the. So how about k equals 1? Well, k equals 1. We have a1, good grief, a to the 1 transpose is a transpose, which of course is a, right? Which is, by the way, a to the 1. So, yay. Okay, so it's true essentially by notation and the assumption that a is symmetric. The base case is true. What's next? Suppose inductively star true for n. Right? Consider a to the n plus 1 transpose, right? Now, by definition, a to the n plus 1 is what? It's a times a to the n, right? That's the definition of matrix power. So then we use your homework problem, the socks shoes identity, with a sub n basically playing the role of b. And so this gives me a to the n transpose times a transpose, right, by socks shoes identity. Then by the induction hypothesis, socks shoes. By the induction hypothesis, this, of course, is a transpose to the n, right? Oh, I'm sorry. I'm an idiot. What is that? Just what? I heard it. Somebody said it. Just a to the n. Thank you. And how about a transpose? Well, that's just a, right? And then it's also true that a to the n times a is still a to the n plus 1. Okay. Admittedly, I have not shown that, but that sort of thing I'll assume here. So consequently, therefore star true for n plus 1, right? Hence, claim follows by proof by mathematical induction, right? There are more things we can say about matrix multiplication. One of the most important things I can tell you about matrix multiplication, other ways to understand matrix multiplication. In particular, this is the column by column rule. Column by column multiplication. And here's how it goes. If I have A times B, and I look at that as A times, like, say, column 1 of B, column 2 of B, column n of B, right? Suppose B has n columns, right? Then you can actually do this multiplication column by column in the following sense. You can say that that's actually A times B1, A times B2, A times Bn. Right. Proving this is one of your homework problems. Okay, but the proof is really little more than just carefully considering the definition of matrix multiplication. Okay. I think my proof is about 3 or 4 lines long. It's not that long. Okay, great. What happens if we take the transpose? What happens if we take the transpose of the column by column rule? What do we get? Yep. Let's see here. Let me write it out. So you're saying we got, take the transpose, we got B transpose, A transpose on the left-hand side, right, by sock shoes. And then this one is what? All that transpose, right? So what's that mean? What happens when you transpose a matrix? What does it do? If you think about it at the level of rows and columns, it changes each column to the corresponding row, right? So each column becomes the new row by transposition. In other words, column 1 transpose is row 1 of the new matrix, right? If you don't believe me, go back to the definition of transpose and prove it for yourself. Or come talk to me about office hours. Either works for me. All right. Now so that's just by definition of transposition. But then we use sock shoes on each one of those. What's that give us? Each row, we use sock shoes on each row. We got ourselves a B1 transpose, A transpose, B2 transpose, A transpose, Bn transpose, A transpose, like so. Yeah? And so what are we looking at here? I mean, this you could also write as what? A transpose times what? What's B transpose look like? It looks like it's B1 transpose, B2 transpose, right? B, I guess I probably should use I used an N, so N transpose. Right. So if you just invent some, just say, A transpose equals to M and B transpose equals to, say, big N, then that gives us the following rule, right? We have N1, N2, Nn, oops, it's kind of awkward, times M is equal to, apparently, N1M, N2M, Nm. So that's the row by row multiplication rule. You notice that it only works if we're talking about the decomposition of the left factor into a stack of rows. Column by column, we're talking about the column decomposition of the right factor in the multiplication AB. They're not the same. You have to be careful, right? Left-handed, right-handed, these are different. All right. Oops. So we're nearing the end of my chapter 1. We're not quite there. I still need to say a little bit more about what's called a nilpotent matrix. I still need to say a little bit more about just how invertible matrices work. And I was wanting to do that today, but it seems that Convo has rained on my parade. I think I can I go for 4 more minutes? If I go for 4 more minutes, we get considerably further down the road. Can I have 4 minutes? All right, if you need to leave, leave. So inverses. Definition. A in our n by n is invertible if there exists B and C in, if there exists B in our n by n. In the notes I proved that the B and C have to be unique, so we can just look at a B. There's B in our n by n such that AB is equal to I and BA is equal to I, where that's that identity matrix I was just talking about. We write B is equal to A inverse in this case. Not every matrix is invertible. Some are, some aren't. And one of our big calculational projects next week will be learning how to calculate the inverse of a matrix. But we need the Gaussian elimination thing to do that first. All right. So I'm just throwing out the terminology so you're aware of the idea at the moment. That said, these are super interesting. Invertible matrices are. An example, a 2 by 2 matrix, A, B, C, D. And this I'll end with this for today. A, B, C, D inverse. The formula for that, guys, is 1 over AD minus BC. You flip the diagonals, and you put minuses on the off diagonal. All right. This is a formula for the inverse of a 2 by 2 matrix. You really should memorize this if you haven't already. But, why does this work? Well, it's pretty simple. If you take this formula, right, and you multiply it by the matrix ABCD, what you'll get back is AD minus BC over AD minus BC for the diagonal components and 0 for the off diagonals. So the proof that this works is just take this and plug it back up into these And you'll see that it actually does work out. So that's the formula for a 2 by 2 inverse. For example, if I had cosine theta, sine theta, minus sine theta, sine theta, cosine theta, if I want to calculate the inverse of that 2 by 2 matrix, it's 1 over cosine squared theta plus sine squared theta, which is what? What's sine squared plus cosine squared? You guys know that. It's 1, right? And if you look at this, this is really cosine of minus theta, sine of minus theta minus, and sine of minus theta, and cosine of minus theta. See, because what I just calculated is the inverse of the rotation matrix, and I showed that the inverse of a rotation matrix is the rotation by minus the same angle, which makes perfectly sense, right? If you rotate by 30 degrees in the clockwise sense, then what's the inverse? It's to rotate by minus 30 degrees, right? Actually, it's counterclockwise, the default. This is actually a rotation matrix in the plane. But anyway, there's an example. Anyway, I shall shut up. Have an excellent weekend. I'll see you guys Monday.